Hello, everybody. Today I will be presenting on my summer experience here at UF Surf. First things first, my name is Chong, and I am with the College of Engineering here at UF. During the regular school year, I attend the University of Michigan, and I major in biomedical engineering. So my summer project has been about the stability and characterization of hydrogels made from D-cell tissues. So the major players during my summer here were Dr. Christine Schmidt, my PI, and Dr. Jorge Mojica Santiago, who was my mentor and postdoc. So before we start, some important definitions that we should familiarize ourselves with is decellularization, or you can hear me say decell. This refers to the removal of cells and maintaining the extracellular matrix, or the ECM, and this is done with SDC, which is a detergent, and DNase, an enzyme. Another term is rheology, which is the study of flow and deformation of a material. This is done with a rheometer, which is what you see on the bottom right. So what is the purpose of my project? Well, for all hydrogel applications intended for human use, we have to go through the step-by-step process of in vitro testing, in vivo small animals, and then large animals before we reach humans. So previously, we have seen that rat scaffolds can be used as a support for growing human cells. If we want to delve into things like injectable technology, we have to take a step back and perform experiments in vivo small animals. So how do I come in? The question I'm trying to answer is how can our materials last in a clinical setting? This means that I study mechanical properties and shelf life. So I perform a lot of rheological tests to observe the mechanical properties of our hydrogels. And the tests include amplitude sweeps, frequency sweeps, and time sweeps, or a temp ramp, or changed. So for frequency sweeps, we have constant strain and changing frequency. Once again, we get our storage and loss modulus. For their temp ramp, we would have our chosen strain from an amplitude sweep and a chosen frequency from a frequency sweep. And this time around, we're going to put it all together and increase temperature in a given amount of time. And this will just give us a better overview of how our material gels. So now we're going to take all of that and apply it to the project. So first I would have to get the material needed to create the hydrogels. And these would be the sciatic nerves from Lewis rats. And you can see approximately where you can find the nerve on the diagram on the right. A total of 48 nerves were harvested, and after harvesting them, we stored them in 0.9% sodium chloride. And now we begin the decell process. So the decell process consists of a series of washes, and usually this would take 4 days. So at the end of all this, I have 43 nerves at 47.9 milligrams. And the reason for the decreased amount is because we had losses along the way between all the washing. So once again, the main question we're trying to answer is how does our material change over time? How does our material change if we store them in acidic conditions versus neutral conditions? We also want to test the time before neutralization or time before usage. We created 4 groups. We have day 0, after 1 day, after 4 days, and after 7 days. And we want to see how our material gels on each day of testing. So at the time of this presentation, we have not completed all days of testing, but I will still present on the data that we still have, starting with amplitude sweeps for the fresh batch in acidic conditions. We can see that the gels have a higher storage and loss, which is something we would expect because gels are less liquidy, they're a little bit more viscous, compared to pre-gels, which have a slightly higher loss in storage because they're in that liquid flowy state. And the blue vertical lines that we see, they indicate the linear viscoelastic region threshold, which means that this is the point where we should start expecting our material to be permanently altered or damaged. So everything on the left of the blue vertical line, our material should still be in the LVR. So when we want to compare specific values, we usually choose a specific strain to compare the values at. The strain that we chose is 0.00464, and this point is within the linear viscoelastic range. So once again, our material has not been permanently altered. The takeaway is there were significant differences in between both groups, pre-gel and gel, for storage and loss moduli. So as I mentioned earlier, because a pre-gel is more liquid than a gel would be, we would expect there to be a difference between the storage and loss modulus per group. And this confirms that because there is a difference between our pre-gel group and our gel group. Moving on to frequency sweeps in pre-gels. This time around, we are comparing our storage times, and we have 3 different storage times. The blue vertical lines indicate the point at which we want to observe our values at, and the frequency that we would like to choose for our temp ramp. So here we have the values of storage and loss per each day of testing. There are no significant differences in between groups and no significant differences within each group. This could be good news because if you want to extend the usage of a batch made on day 0, if the properties are not changing and if the behavior of our material is not changing over the course of 4 days, we can continue to use it. Moving on to gels. As we can see here, the values of the storage and loss modulus are greater than the pre-gels, which is as expected. And then once again at 6.31 radians per second, we see no significant differences between groups and no significant differences within each group. Moving on to time sweeps. So there are 2 ways we would measure how our material gels. The first way is spectrophotometry, and this is basically how much light can pass through a sample over the course of gelling. The second was with the rheometer, and once again, we're just observing storage and loss over the course of gelling. So starting with the rheometer, as we can see, our graphs have similar shapes, but just different values. And the crossover point or gel point is this transition period where our sample is set to start gelling. So for day 1, our crossover point was on average 8.36 minutes, and then on day 4, 7.34 minutes. Moving on to the absorbance readings from spectrophotometry, the data that we get, we will normalize it by fitting it to an equation. We chose a Gompertz fit because it seemed to match the shape of our data best. As we can see, we would get constants such as A, B, and C. And with these constants, we can then determine important values such as the time at 50% gelation, 95% gelation, the time where it reaches its maximum rate of gelling, and what the slope or the maximum rate of gelling is. So on the bottom right here, we have an example from day 1. In orange, we have the fit, and in blue, we have the data. So if we were to average all of our samples on day 1 and day 4, we would get something like this. As we can see, day 4 seems to be a little bit more stable looking, seems to maintain this equilibrium gelling state for a longer period of time. The blue vertical line indicates 5 minutes, and the reason why we have this is because 5 minutes has been said to be the approximate time of gelling. There are no significant differences observed between 2 storage times at time equals 5. So going back to what I mentioned about values of interest, on the left we have day 1 and on the right we have day 4. As we can see, there is a greater variance in day 1 and slightly greater values. I think this is because we have more samples in day 1 than day 4, and this is simply due to not having enough of material or having loss of material along the way or on the day of testing. So at the end of this, why does it all matter? We want to maximize the materials that we have, so we've got to find the best conditions for storing and determine the stability of a material after a given amount of time. And in the long run, this could be more economical, and it could also limit waste. So by the end of the summer, I've learned a lot and I've had lots of fun. I plan on pursuing a PhD in my future. And I would like to thank the SURF program for giving me an opportunity to find myself here and to know what I want my future to look like. I want to thank Dr. Schmidt for accepting me into her lab and giving me an opportunity. Big thanks to Jorge for answering all of my questions, being very patient, and for giving me very valuable advice. And I would also like to thank the rest of Schmidt Lab for being super welcoming and making me feel comfortable and at home. And last but not least, I'd like to thank my roommates because they made sure I was fed and I had a blast with them during my summer.